Hello, everyone. Today, we are going to talk growing hypervisor 0-day with Hyperseed. That is how we use Hyperseed to fast Hyper-V, hypercores. Sort of twisted, huh? So, I am Daniel. I am now a senior security researcher at MSRC. I was member of Keen Security Lab. I have played Pontoon before. I have been speakers to RexCon, Code Blue, and Zero Nights. This is my partner, Shawn.
Good afternoon, everyone. So my name's Shawn. Got my start in security playing war games and CTFs. Mostly played with my school's CTF team, RPISec. Had an opportunity to do some consulting work with Montesano as an intern. I had a ROTC scholarship, so when I graduated, I did 4 years active duty in the Air Force. Separated in the fall of 2017, and then I joined the Platform Security and Vulnerability Research team here at Microsoft. So quick overview of what we're going to go over today. So this talk is really structured in two parts. So the first half, we're going to go over the fundamentals. We're going to kind of lay out the groundwork for what's necessary to understand this space. The second half, we'll actually discuss the fuzzer implementation or mutation strategy, and we'll talk about the findings. So the first question, why did we decide to look into hypercalls? So this really boils down to the fact that both Daniel and I, we were new to the Hyper-V space. So as we were ramping up, starting to kind of understand the architecture, one of the things that kind of stuck out was this interface that was exposed to these partitions. And this interface is accessible from ring 0. So from a hacker's perspective, this is a clear security boundary and an obvious attack surface. Additionally, the hypercalls touch multiple facilities of the hypervisor, so it was a great starting point to learn the internals. And the Hyper-V development team, they produce a document known as the top-level functional specification, the TLFS for short, in short. And this document, it goes into great details on a number of the components of the hypervisor. It describes the hypercall interface, some of their parameters, and so it's really a great starting point. And it's worth pointing out that Daniel and I, we started this work separately. Whenever I joined the team, I began doing code review, and it was through a meetup. I do a biweekly drinking session with the MSRC Redmond crew, and shout out to Overclock. He pointed out that Daniel, he started this fuzzing project in order to, he was looking for guest accessible hypercalls and trying to find bugs there. So that's when I synced up with him, and we kind of progressed the fuzzing work and started looking at different scenarios. So why are we here presenting this work to you today? So in short, we are motivated to secure Hyper-V. The work necessary to do this is non-trivial, and it requires a lot of resources. But we know everyone here has the skills, and that's why MSRC offers a bug bounty, paying up to $250K. So they want to reward you for providing good research. Additionally, we want to generate some energy, provide some insight. So a lot of work has been going on. There's been a lot of past presentations. So we're going to try to keep that going. And I believe it's important for us to document what we did internally. Therefore, you as the external researchers know how to differentiate, find any gaps in our work, and go and earn this bounty. So as I mentioned in the overview, this section is not really going to be a deep dive. Really, we just want to kind of get the base understanding for those that aren't familiar with this space. A lot of the past presentations have discussed the architecture in depth, and we provide links to those at the end of this slide deck. So the main purpose here, we just want to ensure that our terminology is understood and that the base architecture is understood. So when you look at the architecture from a high level, you'll notice that Hyper-V's hypervisor is a type 1 or a native hypervisor. That essentially means it runs directly on the bare metal. The hypervisor is essentially a small microkernel, so it provides a number of services to partitions. This includes scheduling of virtual processors, memory management, interrupt delivery. The hypervisor also handles these hypercalls, which is the main interface that's exposed to guests in order to communicate with the hypervisor. So what are partitions? Partitions are the main isolation unit, and they are composed of some physical memory and one or more virtual processors. The hypervisor is ultimately responsible for managing the nested page tables, and this is what allows the hypervisor to enforce physical memory isolation between partitions. So that way, one partition cannot access memory of another partition. So in this architecture, we have what's known as the root partition, which is also referred to as the parent partition. The root is the host operating system, so this is going to be running Windows. And the root is the only one that has direct access to physical memory and devices, so it's therefore ultimately responsible for managing these virtual machines. So if we look in the root partition, we have what's called the virtualization stack, and there's a number of components. So for each child partition you're going to have a corresponding worker process, the VMWP. And the purpose of the worker process is to orchestrate the life of the VMs and to communicate with the VID. The VID is the virtualization infrastructure driver. And this one essentially provides services such as the partition management, virtual processor management, and memory management services for the partitions. Oops. Jumping forward. So we have two types of child partitions. You have an enlightened partition and unenlightened. Enlightened partition essentially means that it's aware it's running within Hyper-V. It contains some integration components. These components are going to be referred to as VSCs, or virtualization service consumers, and they communicate with something called VM bus. VM bus is the virtual machine bus, and it's one of the main mechanisms for inter-partition communication. And in short, it is a virtual bus device that sets up some channels between the guest and the host, and these channels provide a capability for sharing data and setting up synthetic devices. An unenlightened partition basically has no awareness that it is running on Hyper-V, and any hardware access will need to be emulated. So normally when the hypervisor is running, the virtualization extensions are not exposed, but with nested virtualization, they are, and that way we can create basically a VM within a VM. So the main thing to understand here is with nested virt, not only does it add a new attack surface, so you can think of having a malicious hypervisor, but for us it greatly helps with fuzzer development. So that way I can quickly spin up multiple instances of a hypervisor on a single machine, snapshot it, reset it, and really just tweak our fuzzer. The main thing to take away from this slide is just understanding this terminology. So at level 0, that's going to be your bare metal hypervisor. That's going to manage your level 1, which is going to be your host operating system, which contains the virtualization stack to manage the level 1 partitions. And these level 1 partitions will now have the virtualization extensions exposed, so they can have their own hypervisor to create the level 2. And next, I want to introduce a more recent technology, virtualization-based security. So this was something that was introduced in Windows 10, really to help combat kernel mode malware. And it takes advantage of virtualization technology really to create a new security boundary. And this is what we'll refer to as virtual secure mode, or VSM. And the way this stuff really works is the hypervisor introduces this notion of virtual trust levels. And the main idea here is that a higher number trust level is more privileged, and it can restrict the hardware and memory access of a lower trust level. And VTLs, they are represented as an attribute associated with each virtual processor. So with VSM running, each virtual processor is going to be running at a particular trust level. And this is usually referred to as your active VTL. And when running, the VP can only access memory that is configured for that trust level. And the memory restrictions are accomplished by using SLAT, or second level address translation. These are your nested page tables. So you can essentially program them to portion off pieces of memory and to set attributes on them. So you can set a physical memory range to read only. And you also have the I/O memory management unit, and this is used to provide DMA remapping. So this just ensures that if you have a malicious device, it can't access memory of a higher trust level or another partition that it's not assigned to. So within VSM, we have 2 trust levels. VTL0, which is your normal mode. This is going to contain the NT kernel. And then VTL1, which is your secure mode, and this contains the secure kernel. So the secure kernel, it just provides a minimal functionality for these things called isolated processes. And really, it's not a standalone kernel. It actually relies on the host kernel for things like paging and scheduling. But from a security perspective, and why we're talking about this, we're actually interested in that security boundary. And the secure kernel actually provides some services. So it turns out that this work we did with hypercall fuzzing also applies to this as well. So we'll discuss how to fuzz those. So next, we're going to dive into the hypercalls. Really, we're looking into the basics. We're going to learn how to establish the interface, as well as discuss some restrictions that hypercall handlers will have. So hypercall basics, as I mentioned, this is the main interface to communicate with the hypervisor. There's currently 3 calling conventions supported. You have your slow or regular, and this is just the input and output buffers are going to be passed in via 2 physical guest pages. And the input and output, they're going to be constrained to a page size, and they must be aligned to a natural boundary. The fast hypercall calling convention basically takes its input parameters through general purpose registers, and for this calling convention, it only works for hypercalls that have 2 or fewer input parameters and no output parameters. So this is much faster as there's no memory allocations or mapping involved. For processors that support XMM, you can use an additional 3rd calling convention. So now we can use 6 of the volatile registers to provide an additional 112 bytes of input. And additionally, with this calling convention, you can also accept output. There are 2 classes of hypercalls. You have your simple and repeat. Simple just performs a single operation, and the hypervisor, it tries to enforce that hypercall is complete within 50 microseconds. So for more complex tasks, such as depositing memory into a partition, they have this notion of a repeat, which act like a series of simple hypercalls. So now we can essentially create a continuation. So if it doesn't finish processing, it's up to the caller to tell it where to go and complete the work. Additionally, both classes, most of the time they're going to have fixed size input, but they also have a few hypercalls do support dynamic. And so this is what we call variable sized hypercalls. And you just need to specify what that variable size is, and it's going to be sized to a multiple of 8 within the input value. And the last thing to talk about is extended hypercalls. So this uses the same calling convention as normal hypercalls, and it's identical from a guest VM perspective, but internally, the hypervisor is actually going to pass this on to the parent partition, and these are implemented within the vid. Very few of them exist. Last time I looked, there's 6, and they're very easy to code review, so we didn't bother fuzzing these. So in order to issue a hypercall, you need to kind of understand what the legal environment is. And for Hyper-V, they actually restrict you to the most privileged guest processor mode. So in the case of x64, this will be protected mode with a current privilege level of 0. And if you try to issue a hypercall from an illegal processor mode, this is going to generate an undefined exception. Hyper-V supports a couple different architectures. So they provide this mechanism, a synthetic MSR, to create a hypercall page. So essentially, this will abstract away the difference. And whenever you set this, it's a partition-wide MSR. Whenever you set it, the hypervisor is going to intercept it and actually copy in the code needed. And so we'll look at how to establish this. So here's an example for establishing that hypercall page. And this code snippet is taken from the Linux integration services for Hyper-V. And it's really one of the best open source resources right now for seeing how to interface with Hyper-V. So not only for talking with hypercalls, but it also will contain some of those VSCs for communicating with the synthetic devices. So I'm going to give it a shout out to Alex Ionescu. He recently started blogging about creating a Hyper-V bridge. So he's actually providing code snippets of how to do this on Windows, and he takes a unique approach where instead of having to deal with setting up this interface, he uses an exported routine from the NT. So I highly suggest everyone go look into that. But for those that are interested in creating their own driver, you need to follow some steps. So after you've ensured that you're running on a hypervisor and you check that these synthetic MSRs are implemented, to set up this hypercall page, the guest first needs to register its ID with the hypervisor. And the guest ID is just a 64-bit entity, and this is documented in the Hyper-V specification. After you do that, you just need to allocate a page of memory and then set up that synthetic MSR. And all that it requires is you writing your page frame number to it, as well as setting the enable bit. So the enable bit just says if someone later on tries to recreate this hypercall interface, they can see it's already enabled and just use the existing page. So this is the layout of the hypercall page. So by calling to the hypervisor, not only can you issue hypercalls, but you can also issue secure calls and normal calls between different VTLs and VSM. So as you can see here, this is the Intel architecture 64-bit. And I think the interesting takeaway is that a VTL call is really just a hypercall, and it abstracts the difference. So currently, the call code now is hex 11 and hex 12 for calling and returning. So the normal kernel is going to request specific services from the secure kernel by issuing that secure call and vice versa. And the flow for switching VTLs is as such. And if you recall, each virtual processor has an associated trust level attribute. So by invoking this hypercall, the hypervisor is essentially going to change this attribute. And for those interested, these are the routines I would dig into if you wanted to understand a little bit more about issuing these. So this enter IUM secure mode function is basically the main routine for executing a communication loop. And what this does is it sets up a secure call buffer, which is essentially the bidirectional communication buffer used. So this is what that secure call buffer looks like. And from our perspective of fuzzing, we're only interested in fuzzing the secure services. So this is always going to be a constant value. So that first A, right now it's an enum value of 2. So that's always going to stay the same. Really what we're going to be mutating is the service code and the parameters. So for each service code, they have a specific format, and we apply our format-aware fuzzer to them. So in order to kind of make sure your fuzzer is efficient and operating effectively, it's important to understand what restrictions a hypercall handler can enforce. So these checks, you'll normally find them implemented at the beginning of a hypercall handler. And I'm going to show some code snippets of what these look like. So I understand you guys don't have source, so it's not going to be that helpful. But Sar Amar from MSRC Israel, he recently published a blog post detailing how to get started in Hyper-V research. And one of the interesting things he did is he approached it as an external researcher. So he shows you how to identify the VM exit, so you can see where the dispatch loop is, identify where the hypercall handlers are. So paired with that, and paired with these code snippets, hopefully that'll help speed up and you can recognize what these patterns are. So the first one to be aware of is partitions can have particular privileges. So in order to understand these, we need to understand a little bit about partition properties. So a partition is identified by a unique ID. So across a single instance, it's always going to be unique. If you reboot, it could reuse a different one. And a lot of hypercalls expect you to pass in some type of partition ID, which will basically say, I want to perform an operation against this target partition. So one thing that we utilized a lot is just by passing in the self definition. So it says we want to operate on ourself. Each partition is going to have a set of properties, and you can query them, you can modify them, but the ones we really care about are these privilege flags, and they're represented by a bit field. So these are all possible privileges that a partition can have. They're documented in the TLFS, so I'm not going to go through each one, but I think the key point to understand here is what are the default privileges you have on a child partition, and what's the default for a root. So whenever you first create a partition, it's going to be uninitialized. You're going to have to initialize it. When you initialize it, these are the default permissions you're going to have. So these flags, overall, you can see it's very limited. They actually don't have much. So from a guest-to-host perspective, you're actually limited on what hypercalls you can use. To call out one here, though, you have your access hypercall MSRs. So that allows your guest to set up the hypercall page. But what's interesting, if you use the Hyper-V manager, you actually get 3 additional privileges. So using the Hyper-V manager, the vid is actually going to give you the post messages, signal events, and connect port. And these are used in order to enable VM bus, so that inter-partition communication, and for enlightenments to function. So the root, as expected, the most privileged, it has pretty much every privilege except for the extended hypercalls. So if you recall, the extended hypercalls are forwarded off to the root, so by definition, doesn't make sense. So to do a partition privilege check, this is an example taken from the set logical processor property hypercall. So pretty simple. Basically, you set that bit, call into a routine, it's going to check if your partition has that privilege or not. So as I mentioned, whenever you create a partition, it's actually in the uninitialized state. And when it's in the uninitialized state, there's only about 4 hypercalls that can act upon it. So being aware of what state your partition is in, not only your target partition, but what your caller is important. And so this is actually managed by the object manager within the hypervisor. So this is a reference of how it actually goes about looking into it. So if you walk through the parameters, the first one, the partition ID, as you can see, this is coming from an input header. So this is a parameter, this is an argument provided. This supplies the identifier for the partition to be located. And then the second parameter, this is your condition. So this supplies the conditions for the reference to be taken out. So as we can see here, this is requiring that your target partition is going to be in the active state. The possible states you can have are active, alive, depositable, or exists. And the third one is the required right. So this is the calling partition. So for here, you're going to see whether you need to be the parent, none. So if it's set to none, all privileges are going to be, or all privilege checks are bypassed. And it can also be self or root. And finally, a lot of these hypercalls, they're restricted to the root only. So we're going to do an explicit check for that. But not only that, but you can also have hypercalls that can only be issued from the highest trust level. So this example here is taken from the hypercall to commit a patch. So this is used to apply a hot patch. So in order to do it, you need to be the root partition and at the highest VTL. And finally, the last one, the virtual processor must be in a particular state. So this really only applies to a handful of hypercalls. There's a set that allows you to essentially save your partition state and restore it. These hypercalls are pretty complex, but whenever you want to save state or restore state of a virtual processor, you need to ensure that it's explicitly suspended. All right, so moving on, now we're going to discuss a little bit about our fuzzer. So before we actually talk about the implementation, I'm going to talk a little bit about some of the scenarios that we deployed it to. So this first instance, this is what Daniel worked on initially. So he was interested in finding those guest-to-host escapes. So it's a pretty simple one. You have Hyperseed, which is our fuzzer. So this is what's going to mutate our input parameters. And this passes it on to our hypercall proxy, which is just the driver to issue whatever we give it. So as I mentioned, there's really a very limited set of hypercalls that can actually be invoked directly from within a guest. But what you want to be aware of is, what are the side effects of doing this? So it turns out you have to kind of monitor everything. So not only can you get a crash in the hypervisor, you can get a crash in the host, but you can also crash your own child partition. So you need to be a little bit careful here, So whenever I jumped on board, I was interested in looking for VSM bypasses. So I started fuzzing from the root partition. And this was actually a little bit more difficult because there's a lot of hypercalls that kind of will kill your session before you actually find anything interesting, such as invoking a debugger or asserting. So you can assert a virtual interrupt. And so if you reference your self-partition ID, you end up just killing your host where you're fuzzing from. All right. And so fuzzing from nested. So as I mentioned, we use this a lot for our development stage. The way nested virtualization works is when you issue a hypercall from that L2 root, it's actually going to get sent to the L0 hypervisor first. It determines whether it's going to handle it, which pretty much it's only limited to handling the flushing hypercalls. Otherwise, it's going to forward it back up to the L1 hypervisor. So pretty much every hypercall can get handled from a nested scenario. But now we have more things to monitor for. Not only can you crash the nested hypervisor, but you can crash the host hypervisor and the root. And for the last scenario, this is where we are looking specifically at those secure service calls. So one thing to point out here is that VTL1, it's not a separate VM. It actually lives within your partition, because remember, it's just an attribute associated with your virtual processor. And so here we are specifically looking for crashes within the secure kernel, and there's also crashes of the empty kernel as well. So with that, I'm going to pass it over to Daniel, and he's going to discuss more of the implementation and talk about our findings.
Yeah, thanks, Shawn. And now let me introduce more details. Why choose format-aware fuzzing for hypercalls? I have given a talk about fuzzing CLFS, the common log file system, with format-aware fuzzing techniques on CodeBlue 2016. After that, I also use this technique to generate corpus for KAFL. So it's natural for me to extend format-aware fuzzing to hypercalls. Format-aware fuzzing is effective to bypass fields constraints, and it is easy to scale. At first, you can mutate buffers in coarse-grained fashion. Treat the whole buffer as keywords array, and mutate each keyword with no difference. Then after you get some knowledge of the format, you can move on to fine-grained mutations. For example, you treat the first keyword as partition ID. And since partition ID has a quite smaller sample space, than a generic keyword, then the fuzzing efficiency is remarkably boosted. In similar way, at first, you can only provide fine-grained mutations for the hypercores you have good knowledge of. Leave the other hypercores with default coarse-grained mutations. In this way, you can first let the fuzzer be running and then optimize the mutations step by step. Format-aware fuzzing may overlook some special circumstances by assumptions. Some anomalous input may be missing when fitting into a specific format. Another shortcoming is the dependence on knowledge of input format. For vendor employees like me, it's not a big problem. But for external security researchers, it means more efforts on reverse engineering. But come on, you are a hacker. Do the fucking reverse engineering. So the good news is that Microsoft has already published a very detailed documentation on hypercores. It is called the Hypervisor Top-Level Functional Specification, or simply as TLFS, as well as some debugging symbols, blog posts, and presentations on Hypercore and Hyper-V. It's also worth to mention that there are some generous sharings from external security researchers, like Alex Young's school with his HDK and Hyper-V bridge. Besides the resources mentioned above, you can keep accumulating knowledge during the fuzzing process. The fuzzing itself is a process of learning. The format-aware fuzzing is more like agile style development. In each iteration, you can gain some insights, and then you can add further adjustments. Exceptions like crashes are expected as a fuzzing output. Root cause analysis on those exceptions can help you gain more knowledge of the fuzzing target. With enough knowledge of the relationship between the input buffer and a specific type of exception, you can introduce bypassing logic to make your fuzzer be immune from an already known exception, which may help bypass some traps and reaches to the deeper codes. Mutations is important to fuzzing efficiency. How to mutate? There may be different answers to different people. No matter how complicated the input buffer is, it can be splitted into primitive data types. Mutating those primitive data together is a way to mutate the whole input buffer. So here, we implement 5 mutators for primitive data types. The first mutator is a random mutator, or random generator. It will generate a random integer utilizing C++'s random library. Here we take keyword as an example of primitive data type. A random keyword will be generated here. And for demonstration purpose, I manually choose a keyword as the random output. The diagram on the right side is used to illustrate the layout of this keyword. So each keyword is comprised of 8 bytes, and each byte is divided into 8 straps. So each strap stands for a bit. Solid strap stands for bit 1, while hollow strap stands for bit 0. The second mutator is bit sliding mutator. It will circularly shift n bits in the left direction. N is a random integer in range from 0 to 64. Here we choose n to 45. So the current sliding mutator will take the output from last step and circularly shift it left by 45 bits. And the third mutator is the swap half mutator. It will split the keyword into 2 D words and swap them. You may already notice that swap half is a special case of a sliding mutator. We make it a standalone mutator since it preserves the alignment in the next lower level. And the fourth mutator is a bit flipping mutator. It will flip a bit at random position from 1 to 0 or from 0 to 1. Here, we choose another random position to 47th bit, and it is flipped from 1 to 0. The last and the most interesting mutator is the mask mutator. This mutator is inspired by the observation that actual memory content looks sparse. Take a keyword as example. It may be a composition of 8 bytes, or 4 words, or 2 D words, or even some bitwise flags. It can be interpreted in different ways, and some of the bytes are expected to be 0 in specific interpretations. Mask mutator provides a way to erase random bytes from the output. A random byte m is generated to determine which bytes to be erased. Here, m is chosen to be 0xA3. Since each byte is comprised of 8 bits, and each keyword is comprised of 8 bytes, I expand each bit in m into a byte as a 0 or 0xFF. Then the byte m is promoted into a keyword. Do bitwise AND operation with this promoted keyword can help erase random bytes to 0. All right, now we have 5 primitive mutators, and they can be layered one above another to form a more advanced mutating logic. So here, I implemented a mutator dispatcher. It overlays the primitive mutators together according to a random byte, which renders a more complicated mutating logic. Both the primitive mutators and the dispatcher are implemented with C++ template. This implementation provides a uniform mutating interface, and this uniform interface can be directly applied to different primitive data without explicitly specifying the data types, which makes writing a specific mutation much easier. Then let's see the Hyperseed components. We already know that the hypercore proxy.sys is a kernel driver that helps issue hypercore. And we already have 5 primitive mutators and a uniform mutator dispatcher interface. Then we can start to write hypercore mutations. Here, I use divide and conquer way to organize the mutations into a stack. Generic mutations can help mutate general parameters like hypercore calling conventions and hypercore classes. A default hypercore mutation is provided for coarse-grained mutating, which means splitting the input buffer into an array of keywords, then mutate each keyword in the same way. C-based mutation is a default hypercore mutation. Why we need specific mutations for different hypercores? With default mutation, we treat every keyword in the same way. But for a specific hypercore, the input is supposed to be fitting in different data structures. Different fields have different meanings, like partition ID, like VTL levels. Assigning type to a piece of buffer can remarkably narrow the sample space, which makes loss input, survives basic checks, and reaches to deeper code logic. In this way, the format-aware fuzzing is more effective than dummy fuzzings. How to write a specific hypercore mutation is the same as splitting the whole buffer into a combination of different primitive data types, then adopt the primitive mutators upon them. After we have enough knowledge of a specific hypercore's input, we can do the splitting precisely. So here, I also want to highlight 2 interesting hypercore mutations. The VTL call mutation is used to fuzz the virtual secure mode secure calls into the secure kernel. That is to say, fuzzing from the VTL 0 and want to break down the VTL 1. And the other is C-post message mutation. It is used for fuzz the scenic messages for interpartition communications. Those 2 hypercores have very complex input formats, and no wonders we got amazing findings from them. I will talk about findings later. So let's see an example of a specific hypercore mutation. The flash virtual address space hypercore. It invalidates all virtual TLB entries that belong to a specific address space. There are 3 parameters in the input buffer: address space, flags, and processor mask. The flags is a keyword, but it is actually a bitwise composition of several binary options. Only the 3 lower bits are valid. Other bits are reserved to 0. The fuzzing efficiency for this specific hypercore will be remarkably boosted by enforcing this format rule. And several macros here are defined to make the mutating codes neat. The macro BM is a wrapper for mutator dispatcher interface. It can be directly applied onto a primitive data field, regardless of its actual data type, and thanks to C++ template. So after introducing so much, you may wonder what we get from Hyperseed. About 1 year ago, I just started my role at MSRC, and I was expected to contribute to Hyperway security. So I initiated the Hyperseed project at the end of February last year. It took me 2 months to find the first vulnerability. Then I open sourced my project internally within Microsoft, and Shawn starts contributing to Hyperseed since the end of July. He has added lots of specific mutations and expanded fuzzing scenarios. He has also found several vulnerabilities between July and September. At the same time, he also helped integrating Hyperseed into our internal code repository. And then, after an inspiring conversation with Saarma in October, I started fuzzing secure kernel. It took me another 2 months to find several interesting VTL 0 to VTL 1 vulnerabilities. More findings are expected in the near future, but we would like to share with you this idea now. Hyperseed and formatted web fuzzing is one of the useful ways to find Hyperway vulnerabilities. Well, this is the findings so far. So this diagram shows the types and impacts of those findings. The red vector indicates it is an elevation of privilege vulnerability or remote code execution vulnerability, while the blue vector indicates it is a denial of service vulnerability. The starting point is where Hyperseed is deployed, and the ending point is where the vulnerability can be used to attack. And the length of each vector has nothing to do with impact. Only the starting point, ending point, and color matters. So you may want to know how much are those findings worth if they are reported from external security researchers like you guys to my MSRC. Yeah, let's see it. So there are 2 of the findings are qualified for Hyperway bounty. And you can find more details about Hyperway bounty through this link. The RCE vulnerability from guest to host is qualified for Tier 1 RCE category. It can be worth as much as $200,000 US, even without exploitation. And the DOS vulnerability from guest to hypervisor is qualified for Tier 1 DOS category. It is worth another $15,000 US. And there are 7 of the findings are qualified for Windows Insider Preview bounty. The 2 EOP vulnerabilities from host to hypervisor can be used to bypass VSM secure features. And the 5 EOP vulnerabilities from VTL 0 to VTL 1 also be used to bypass the VSM secure features. So each of those 7 vulnerabilities can be worth as much as $20,000 US if they are reported with high-quality report. So you may want to know what makes a high-quality report. Then you should check our blog post on report quality definitions in the appendix. Then let's see the guest host RCE vulnerability. It has been given CVE number 2018 and 8439. This vulnerability was found in last May and was fixed in September. It is a use after free vulnerability, and it is less likely to be exploited. And that's why it didn't get the highest bounty. And this vulnerability is found by fuzzing HV post message hypercore. This hypercore is well documented in TLFS, so be sure to check it. It is used for interpartition communication through synthetic interrupt controller. The posted message will be first copied to hypervisor's internal queues, and then copied into the target partition. This is one of the very basic interpartition communications, and even VM bus is built upon it. This vulnerability can be reproduced with the following steps. First, run the Hyperseed inside a guest VM and keep fuzzing HV post message with open channel and closed channel as a channel message type. Then manually reset the guest VM from host Hyperway manager can make the host crash. So at first sight, it seems host is dosing itself. But after carefully diagnosis, it is a use after free, and it can be triggered totally within the guest. This is part of the crash dump. Apparently, the memory location being referenced has already been freed. So the referenced memory is inside of the monitor page. It is the pending bits inside of the trigger group. The monitor page is part of the monitored notification facility. It is used to establish a hypervisor monitored unidirectional notification channel between two communicating partitions. The monitor notification parameters are stored in monitor pages. You can find more details about monitored notification on TLFS. So here we only need to know that this vulnerability causes the monitor page to be referenced after it has already been freed. The monitor page will be allocated when initializing a VM bus connection. It will be freed when resetting or destroying a partition, or failing VM bus connection. A reference to the monitor page will be cached internally to support interrupt, which eventually will be carried out by calling HV signal event using the parameters stored in monitor page. If the channel is not opened properly, it still holds the reference without clearing it. Then further access to the cached reference after being freed leads to UAF. And the fix is pretty simple. It checks the open result and clears the reference if the channel is not properly opened. So as you see, Hyperseed is still under development and far from complete. The format-aware fuzzing nature makes it not easy to be reused with little rework. But we still want to share with you this idea and approaches of fuzzing hypercore. It may give you some hint and inspirations. And in the future, we will keep improving the Hyperseed and format-aware fuzzing. We will investigate ways to combine the power of entire processor tracing, AFL, and Hyperseed into a coverage-guided fuzzing framework. We will publish more details on other findings after they're being patched. And we are planning to open source a modified version of Hyperseed, after removing dependencies and sensitive information. So in near future, I guess. And we will try to extend format-aware fuzzing to more targets. And thanks to our teams, and as well as Hyperway team. So please don't forget to check the appendix for valuable research on Hyperway and Hypercore, as well as some useful public resources. So those are the valuable references you can check if you want to do Hyperway security research. And those are the useful public resources you can use. So the first and the most recommended resource is the TLFS. It includes very detailed information about Hypercore. You can also see a lot of Hyperway internals, like intercepts, interpartition communications, and what your secure mode is central. If you want to learn Hyperway internals, it is the best materials for you. Second is the debugging symbols for selected set of Hyperway executables. It can be used to do the reverse engineering. And you can find lots of function names rather than the exported ones. And the third one is a Linux integration service. It is available on GitHub. It contains some structure definitions and even some functions to help you directly issue Hypercore. The fourth HDK is reversed by Alex. It contains many structure definitions, which should be useful for writing Hypercore mutations. And the last one is the report quality definitions. So if you want to get more money for WIP bounty, then study it. That's all for our talk today. Thanks for your time. Any questions?
Yeah, go shoot. And for the rest of us who don't have questions, please stay seated until the time's up, so we can answer the question without a big commotion. That.
Which collection of hypercalls would you recommend us fuzzing?
Okay, I've already highlighted two. So the first one is for fuzzing VTL0 to VTL1, the secure calls, and the other is post message. So yeah, and another thing I want to mention is that the site you can call from guest partition or from root partition is different. There is very limited set of hypercalls are accessible directly from the guest, but there's a lot from the host, almost all. So.
Hello, thanks for the talk, it was really cool. You mentioned that future work will include coverage-guided fuzzing.
Yeah.
Is there already progress on this?
Yeah, so now the problem is there is no public solutions for supporting, supporting Hyper-V with the entire PT. And now there are some internal efforts working on that. So yeah, we're doing on it.
Additionally, I've played around with doing binary rewriting, and so I've had some success that way. It's just a matter of fine-tuning it.
Why do you have source code access? Why don't you compile it with coverage-guided instrumentation?
Well, that
Yeah,
requires our
that.
compiler to support that first.
Anybody else I'm not seeing? Okay, apparently we're done. Then let's get another round of applause.